Alright, final slide. This has been interesting. We've got an elevator example. We're given a ball thrown vertically upward from a 40-foot level, initial velocity 50 feet per second. Same instant, an open elevator passes the 10 feet level, moving upward with a constant velocity of 5 feet per second. So we got two things moving again, and we want to find out where and when they meet. And so think about that for a second. We've got it drawn out over here. Elevator, 10 feet, velocity 5 feet per second. That's constant velocity. So that means acceleration is 0. We don't have to factor in a change in speed. This one has a 40-foot height start, so we've given a datum down here, a reference. We'll use positive as up. 50 feet per second initial velocity. The key here is acceleration is free fall, minus 32.2 feet per second squared. Alright, so let's think about this. We want to find where and when the ball hits the elevator. Got this modeled in Excel, so let's look at that really quickly. You guys are learning Excel in ef105, so this is a good example of that. Looks right. So I've got two windows here. One is at the end of the module on Excel, you will learn a little bit about animations, but we've got an animation here where we've got some images that we can move relative to numbers in a chart. So the key here is our chart. We've got elevator, time, position, velocity, acceleration. Okay, and I'll even click on those. Let's see, scroll down just a little bit so you can see the equations up here. Okay, up here in the formula bar. So there's our initial position, our initial velocity, acceleration, and then we've written equations that are our equations of motion, okay, for these based on delta t and let's see, acceleration and initial velocity. Alright, same for the ball. Okay, minus 32.2 acceleration, 50 and 4. So and then we've copied and pasted these equations all the way down. So we've created increasing time increments of 1/10 of a second just to get something here. And again, you could actually look through this chart and sort of find where the positions, which is column C and column F, become close to being equal. Alright, so it's going up, coming back down. Looks like somewhere maybe about right in here. Okay, they become equal and pass each other. So we expect an answer of around 3.3 or 3.4 seconds. We could graph this out. I believe I've got a graph down here. I thought I did. Let's see, where did it go? Alright, so here's our graph of, move it over just a little bit for you. The elevator position and the ball position. The ball position constant, the elevator position constant velocity. So this is position in meters versus time in seconds. Okay, so constant velocity. The position would be increasing at a constant rate, so it's going to be a straight line, graph like that, starting at 10. The ball is constant acceleration. We have an initial velocity, the slope of this line, 50 meters per second, I guess it was. Actually, this should be feet. That's the wrong label. 50 feet per second. Okay, acceleration of gravity. So this is going to be a parabola. Up here the velocity is going to be 0, the slope. Okay, right there it's going to be 0. And then we can see where these two curves intersect, since we plotted the position of both versus time. is what we're looking for. So the height, the time I said is going to be around 3.4 seconds, and the height is going to be around 26 or so feet. So let's see if we can work that out with numbers now. I can run this simulation since we have it here. It's set up to, whoops, it's set up to have the numbers over here, and then I can step through this. Alright, and this is actually highlighting the current, so at 0.7, the ball's still going up, the elevator's going up slowly, and so forth. So I could scroll up here and try and find about when they meet. So somewhere right in there. Just a little visual to see what's happening. Alright, close out Excel. Let's work the numbers here. So work this, let's write an equation for the position of the ball. So we'll label that S sub B, and it's going to be the initial position of the ball. So I will use 2 for when they hit and 1 for initial. And the initial velocity of the ball plus 1/2 the acceleration of the ball times the time squared. And I forgot the time in here. Okay. So I scrolled up there. Let's get back to where we should be. Sorry about that. Alright, the same thing for the position of the elevator. So S elevator 2 is equal to S elevator at 1 plus the velocity of the elevator at 1 times T plus 1/2 the acceleration of the elevator T squared. Okay, why did we do this? Well, we know that we want to find the position or the location where the two positions become equal. So we look for an equation that has most of the things we know in it. So let's underline what we know. We know the initial position of the elevator, we know the initial ball, we know the initial velocity of the ball. We don't know the time. We know, don't scroll on me there, we know the acceleration of the ball. Okay, likewise we know all that information about the elevator. So the only thing we don't know is the time. Okay, but we do know that these two values, that's what we want to find, those two values, the time at which those two values will be equal. So writing two equations like this, we can set them equal to each other and solve for the one unknown value, t. Alright, so let's do that quickly. Let's see, so the acceleration of the elevator is 0, so that term will drop out. So I'm going to have the acceleration of the ball initially plus the velocity of the ball times time plus 1/2 the acceleration of the ball times squared, and that's going to be equal to the position of the elevator initially plus the velocity of the elevator initially times time. Alright, plug in some numbers. We'll use reference like we set up on the right here. The position of the ball was 50. The velocity of the ball was, excuse me, this should be careful here. Oops, come on, eraser. Get to an easier color to see too. Position of the ball is 40 feet. The velocity of the ball is 50 times some unknown number of feet per second times some unknown number of seconds plus 1/2 minus 32.2 feet per second squared times t squared is equal to, and let's see, let's just get rid of that. Yeah, position of the elevator was 10 plus 5t. So now we're back down to algebra, solving quadratic equation for t. Okay, and we will get, let's see, 3.35 seconds, or a minus, number went away on me, minus 0.556 seconds. Minus 0.556. Okay, if we remember our parabola, or our graph, so I can call that up real quick, maybe. We are looking for this point, but there's also another intersection point out here somewhere. Negative time doesn't really make sense, but mathematically those two curves do intersect. That's our negative answer. There's our positive answer. Alright, so there's our time when the ball hits. Okay, the position is going to be really easy because we can use now either one of these equations. I'm going to use the position of the elevator because that's a little simpler. Now that I know the time, I can find the position of elevator 2 is equal to initial position plus its velocity times our 3.35 seconds. And that's going to be 26.8 feet. Alright, so I'll highlight the answers here. 3.35 seconds, 26.8 feet. I would have gotten this same answer if I plugged this time back into my ball equation right up here, right here. Okay, would give me the same exact answer. It would be a good way of double checking. Alright, we'll finish up here. Let us know how this works out, and hope you have a good weekend.